Hello, welcome back. We start with some concepts of probability. So hopefully this is a review, and I'm putting more value on intuition than on clean mathematical definitions. I mean, there are also different ways to define what a probability stands for. Mathematically, the most rigorous definition is based on Kolmogorov's axioms, and probability is a mathematical discipline where you can derive theorems and so on. For beginners, it's more important to obtain an intuition, and the definition I present is based on a relative frequency. So that's probability. In statistics, probability theories then apply to problems of the real world, and sometimes there's disagreement in the second kind, so how to apply probability to problems in the real world. In particular, there's this the two sides, the frequentist statistics and the Bayesian statistics. But that's not the topic of today. So we start with an example. So let's assume that there are n tilde equals 50,000 students in Munich. Just happens to be 50,000. The set is called the population. The size of the population often is assumed to be infinite, but in this case it's finite. Formally, I put all 50,000 students in an urn, or in computer science you might call it a bag. Then I randomly select a student out of this urn, and this process of randomly selecting a student is called an atomic event or an experiment, and defines a random process, because it's sort of random which student I will pick. The selected student then is an outcome of the experiment. So I will pick a particular student, and this student is then the outcome. Of course, any particular student will be picked with an elementary probability, 1 over n tilde. So if I don't cheat and I don't have any other way of being unfair, any one of these students has a probability of being picked 1 over n tilde, so in our case 1 over 50,000. If we do repeat this experiment n times, this produces a sample. So in our way or nomenclature, it would be the training data set. D, so we call it D, of size n. So we repeat the experiment n times. And then we are studying the sample, and this can give us then insight about the population. And this process of deriving information from the sample and then making statements about the population, that's called statistical inference. There are some fine points. So there's sampling with replacement. So if I picked a particular student, I return the student to the urn. So in principle, I could pick the same student twice in the sample, or several times, because I always put the student back into the urn. Then there's sampling without replacement, where I do not return the student to the urn after the experiment. The analysis of the first case is easier, and would also be the same if so both would be the same if the sample is or the population is infinite. But so in case you're wondering, we would be concerning with the sampling with replacement, where I put the student in our case back into the urn. So now, so this was a random experiment, and now we're talking about the random variable. So a particular student has some attributes, for example, height. When we just say 5 classes, tiny, small, medium, large, and huge. So then we call h, the big H, the random variable, the height. And this random variable has these different states. No? So h is tiny, small, medium, large, and huge. So a random variable is sometimes defined as a variable whose value depends on the result of a random process. So more formally, they say sometimes a function of the outcome of the random experiment. But let's consider something something you can measure on the entity you've selected in the random process. Thus, in each experiment, I measure a particular age. No? So every student has a particular height. So I take a student out of the urn, I measure the student's height, and then I put the student back into the urn. That's the process. Now we're coming to the concept of the probability. So the probability that the randomly picked student has height h, so the random variable h, assumes the value small h, is defined. So this is defined as p of h equals h, so capital H equals small h, and that's the limit if we repeat the number of or the size of the sample goes to infinite, and we divide the number of times that we measured height small h by the sample size n. So if 10 out of 100 would have size tiny, then n tiny, n subtiny would be 1/10. And by this definition, the probability is automatically smaller or equal 0 and smaller or equal 1, because n is the maximum number of an h could assume. So NH is the number of times that a selected student is observed to have height big H equals small h. And so here we have this transition to sample size goes to infinite in this formula. In practice, we only have a finite number of data points, so we are estimating this probability as the number of h, and h divided by n from the finite sample n. No? And this, so here we put this hat on top for an estimate. This would be our estimate of the sort of true underlying probability that large h equals h. In statistics, one is interested how well this estimate is to the true probability. No? So the estimate based on the sample of size n is how close it is to the true one, and under some assumptions you can estimate the error or the difference between these two values. Of course, and you always have to remember, I mean, the definition of a population was critical. No? So we defined it as being the students in Munich. If it's a student in another city, these definitions or these probabilities, not the definition, but the probabilities would give you different numbers. So sometimes people disagree on certain things because they're just talking about different populations. Thus, the populations plays an important role in statistical analysis, and you have to be aware. And ideally, as we've discussed here, you completely randomly pick your data points or your sample. If you don't do it randomly, then you introduce maybe a bias in your analysis. So again, the difference between statistics and probability. So probability is a mathematical discipline developed as an abstract model, and its conclusions are deductions based on axioms. So you have axioms and you derive theorems. In particular, Kolmogorov's axioms. Statistics deals with the application of the theory of probability to real problems, and its conclusions are inferences or inductions based on observations. So this definition I found in this book from Papoulis, Probability, Random Variables and Stochastic Processes, which I recommend. And as I already mentioned, frequentist or classical statistics and Bayesian statistics apply probability in slightly different ways. We will discuss this later, not this time. Oh, maybe a little bit less this time, I don't know. So this was simple. We had one thing we were measuring. This was the height of the student. But now we are measuring a second thing, the size of the student. So the weight or size of the student, S. With weight attributes, very light, light, normal, heavy, very heavy. S is a second random variable, and we can similarly define the probability that S assumes S as the limit sample size to infinite ns divided by n, where ns is the number of times that the size is S for the student we pick. But now it also gets more interesting. So we can also define what is the probability that the height is h, small h, and the size is small s. So we are looking now at two random variables, and that's naturally the limit n to its infinite, the number of times that a student has the height h and the size s divided by the number of students in the sample n. And this is called the joint probability distribution of h and s, height and size. Now typically there's some correlation, so tall people are a little bit heavier than light people. But okay, this is the definition. No? So now it gets interesting, because now we can also discuss the dependency or the relationships between random variables. We can also, first of all, let's say we have this quantity, or an estimate of this, and we are interested in just one of the probabilities, so height or size. How do we get that? That process is called marginalization. So it's the so let's say we're interested in the height, probability of a height. Then we are summing over all counts of height and size divided by the sample size. And this is the same as our the probability of height and size when we sum over all sizes. So this marginalization is a very important operation in probability. And hopefully here it's easy and you can easily understand what's going on. So it's this is called the joint probability of height and size. And we sum over, in this case, the second random variable, the size or the weight. And that gives us the probability of the height. And you can see it by this plausible formula here. And this process is called marginalization. So I can calculate the marginal probability from the joint probability without having to go back to the counts. I can do it when only based on these probability values. So another quantity which is of interest is it's called the conditional probability. And that really tells us something about dependencies. No? Let's assume that I'm interested in the probability distribution of size for a given height. So I'm only, if I sample somebody and this person doesn't have the height, I just put them back. So first I look at the height of the student, and if the student has the right height, then I keep him. Otherwise I put the student back, he or she. Now I simply need a different normalization, because I always put the ones back which don't have the correct height. So and this is called a conditional probability distribution. So the probability of size given height is the limit of the counts. How often do I observe a person with this height and this size divided by the number of patients which had this height? Because I'm putting the other ones back which didn't have the correct height. So I essentially replace an S with an H. So I count the co-occurrences, but I normalize by an H. So these are the co-occurrences. This is also an extremely important operation. And hopefully today or now it still looks obvious and simple. Because this is, now you can think of the right part of this conditioning sign here as the input and the left as the output. So the input is the height and the output is the size. But I don't just get one value out, I get the whole probability distribution out for size, for every height. And for every height, this can be different. And if I look at this definition and use the formulas before, I can see that the conditional probability of size given height is the same as the joint probability of height and size divided by the probability of height. Sometimes this is also considered the definition of a conditional probability distribution. But we derived it intuitively. It means I only consider the students with a particular height h, and then I look at the probability distribution of size. And this can be calculated by this formula, which is, again, very, very important. Now here again, height would be the input and size would be the output. Yeah, conditioning is closely related to the definition of a population, because if I consider this conditional probability, it would be the same as P of S if in a population which is restricted to students with age. So I'm sort of reducing the population I'm interested in by conditioning. So it's closely related to changing the population I'm considering. And from the definition of the conditional probability, I get another important result. So let's just multiply both sides here with P of H. Then I get P of H S is equals to P of H times P of S given P of H. P of S given H, right? And so this is called the product rule. And so this is the same equation, just that I put this on the left side. So the probability for the joint probability S and H is equal to the probability of H given the probability of S given H. And due to symmetry, it's also the probability of S multiplied by the probability of H given S. Again, a very important rule, but it's following from the definition of the conditional probability. And by why is it so important? Because it permits me to decompose probability distributions of many random variables into a lot of conditional probability distributions. So the first one is this times this, so P of x1 times P of x2 given x1, then P of x3 given x1, x2, and so on, until the last one, P of xm given all its predecessors. And this is the same as the joint probability of all these random variables. And this will be used in Bayesian networks, for example. It's very important. So there's one more, maybe the last general important formula. So you might wonder if I have the probability of size given H. Is that the same as the probability of H given S? So can I just flip these two numbers and the probabilities are the same? No, that's not possible. It's not true. The exact relationship is given by the famous Bayes formula. And here, I mean, we start with these definitions of the conditional probabilities. P of h given s is the same as P of h and s divided by P of s. And the other way around, P of s given h is the same as the joint divided by P of h. And so if I start with this formula, I remove this part by substituting the product of P of h by P of s given h, and right away I have a base formula. No? So I can write it in this way and this way. So here we see directly that you cannot just change the order. So P of h given s is the same as P of s given h times P of h divided by P of s. So you have to correct it by this quantity. Or more commonly, you write it like this. It's P of s given P of h times P of h given by P of s. So always the stuff on the right side appears on the same side of the quotient symbol here, and the other one below at the denominator. So typically you remember this formula. But here it's clear that you cannot just exchange these two things unless these two equations, these two probabilities are the same. So this is the correct formula. And again, base formula is extremely important, and also the basis for Bayesian statistics. So if we have two random variables which are independent, then we can first decompose it again into P of s times P of h given s. But if P of h doesn't change with s, so the probability of height would be independent of the size of a person, then we can remove this conditioning sign here, and we get the product rule. So not the product rule, but the factorization. So the joint probability is the product of the individual probabilities. But this is only true if the two random variables are independent. Yeah, another important formula. So to summarize, and to sort of also to show that these formulas are essentially not that difficult or complicated, but they're all extremely important. So the conditional, so here I wrote it a little bit simpler without the capital ones, and people write these things always in different ways, but this is one possible way. So P of y given x is P of x comma y divided by P of x. P of x comma y is the probability of x given y times P of y, or it's the probability of y given x times P of x. Then the chain rule in any order, so you can also change the order here, doesn't matter. But let's just keep it in this way. Then it's P of x1 times P of x2 given x1, P of x3 given x1, x2, until P of xm given all its predecessors. Then Bayes' theorem, P of y given x is P of y comma P of x comma y divided by P of x equals P of x given y times P of y divided by P of x. And then marginalization, P of x is the probability of x and y divided by y. And for independent random variables, we have this factorization. So the P of x comma y is the same as P of x times P of y. So here's an example where we are using these equations for inference in an expert system. Let's assume there's some joint probability distribution of I, F, and S, where I stands for influenza, F stands for fever, and S stands for sneezing. And we are interested in the probability for influenza, so for the disease, when the patient is sneezing, but the temperature is unknown. So unknown means we marginalize out. and this inference is conditioning. So we are interested in the probability for the influenza given the sneezing. So I'm interested in this probability of influenza given sneezing. I expand it using the definition of a conditional probability in the probability of influenza and sneezing divided by the probability of sneezing. Then, so I have to, next I have to calculate these two terms. How do I get this one, the probability of influenza and sneezing, given that this probability is known? So we're assuming that somehow we know this probability. So this is written here again, probability of influenza, fever and sneezing. And since I'm interested in the dependencies without the temperature or the fever, I have to integrate over the fever variable. So this is just true or false. So there are two states here, true or false. So I form the sum here with I equals 1 and S equals 1, and with different terms here for the for fever. So yes or no. Yeah. And so this gives me this part over here by marginalization. Then if I have this term, then but I'm interested in this one, then I have to do another marginalization. So I take this expression, which I just derived, and sum over the influenza variables, and then I have the probability of sneezing. And then I divide this number by this number, and I get my desired conditional probability. So it's quite powerful, and in a way it's simple. And this is the basis for inference in Bayesian networks, which we will cover later. Then now I'm going through some further definitions, which will be important in the remaining parts of the lecture. So there's something called the expected value, and it's something like the mean of this value. So it's the explicitly you're summing over the values of xi, and you multiply it with the probability that x assumes this value xi. And so if you obviously if you sum over all these terms on the right side, it adds to 1, but you weigh it by the value of this random variable. And it's sort of what you mean, what you would expect it to mean. It's like the average thing, like the average height, the average weight, the average value of the random variable. And this is called expected value. Then the variance sort of indicates how much the random variable or the realization of the random variable sort of varies around its mean. So we sum over all possible values of the random variable, and we take the value minus the expected value of this random variable, and take the square of this expression and multiply it by p of x. So the variance is high if there's a lot of variations across the mean, and the variance is small if the variation around the mean is quite small. Another important thing is the standard deviation, which is the square root of the variance, because the variance as a number is sometimes difficult to interpret, but the standard deviation is sort of a distance, so you have a feel for how much the scattering is around the mean value. Then if we have two random variables, x and y, we can define the covariance, and it's the sum over I and the sum over j of the expression xi minus the expectation of x times yj minus the expectation of y multiplied by the joint probability x and y. And it sort of indicates if they are independent, these random variables, or if they're very dependent. If they're very dependent, the covariance is very much far away from 0. If they are independent, then the covariance is 0. And another important quantity is the covariance matrix. So it's a 2 by 2 matrix. And on the diagonal, we simply have the variance of the two random variables. And on the off diagonal, we have the covariance of these two random variables. And this is automatically a symmetric matrix, because this is 2 times the covariance, but the diagonal terms, of course, can be different. Here's some useful identities. So the covariance of x and y is the same as the expectation of the product x times y minus the product of e of x times e of y. And you see if x and y are independent, then this is also the product. The product minus the same product gives 0. So if they're independent, the covariance is 0. And this term, e of xy, is sometimes called the correlation. And so in the correlation, you multiply and to the expectation, whereas in the covariance, you first subtract the mean. Then there's the Pearson correlation coefficient, which we have already encountered. And the naming is a little bit confusing, because it's the covariance divided by the square root of the variance of x and the variance of y. It follows also from this equation. So if you set x equals y, so the covariance, in this case the variance of x, is the expectation of x squared minus the expectation of x to the square. This follows from this equation directly. And also, if we have a function of x, the variance of a function of x is the expectation of f of x squared minus the expectation of f of x squared. So you can use these equations maybe now as a reference table to look it up whenever needed. Whereas the first equations I think are really important, and you should really learn them if you don't know them already. More useful rules if it's for two random variables and they can be correlated. The expectation of the sum is the sum of the expectation, or the expectation of x squared plus y squared is the expectation of x squared plus y squared plus the expectation of y squared. And for the variance of the sum of two random variables, so the variance of x plus y is the same as the variance of x plus the variance of y plus 2 times the covariance of x and y. And the variance of the difference, x minus y, is the variance of x plus variance of y minus 2 times the covariance of x and y. So again, now we are getting a little bit advanced, but these are equations we will need later in the lecture. So let's say we have a random vector. So W has several dimensions, and we know the covariance. So let's even assume that the mean of W is 0. But the components of W are not completely independent, and this is specified by a covariance matrix sigma sub W. Now remember, covariance matrix was this beast over here. In this case, we would have W1, W2, W12, W12. But this can also have more dimensions, more than 2, no? But it has the same structure. On the diagonal are the variances, and on the off diagonal the covariances. So if we have this, so we know that W is let's say 0 mean and has this covariance matrix. Then we're forming a linear map from W to Y. Yeah. So an A is some arbitrary matrix. it's a fixed matrix, non-random. Then let's say W has mean 0. Maybe I should add this to the slide. Then Y also has 0 mean, and I can also calculate I can derive the covariance of Y. And so Y is also a vector with several dimensions, and it's you can calculate it by this formula, and this formula we will use in this lecture. No? So the covariance of Y is the covariance of W, and then you multiply it by A on the left side and by A transposed on the right side. Now, so this is how the covariance on W is transported into the covariance of Y by this formula. So far we dealt with discrete random variables, so they could only assume a fixed number of states. But it's straightforward to generalize this also to the continuous case when the random variable can assume any value out of an interval, for example. And then we are talking about probability densities, and also a change from P to F. Sometimes they use small p instead of F. And it's sort of defined as the limit that delta x goes to 0. And here in the denominator we have the probability that the random variable is larger than x and smaller than x plus delta x. So the probability that x is between a range, so larger than a and smaller than b, is the integral of f of x of this function. And there's also something called the distribution function, which is the integral from minus infinite to x of this density d of x. And this is the same as saying that the probability of x is smaller or equal x. So it's a certain limit, and it's not so important that you exactly understand what's going on here. I mean, the important thing is the meaning of the probability density is extremely close to the meaning of the probability distribution. And even more importantly, you can apply basically all formulas we have learned so far also for probability densities. Now, the conditional probabilities and the conditional probability density and base formula can be applied and so on. But in a continuous case, it's defined as in this limit. No? So in other words, we don't have to care really. Are we talking about a discrete random variable or a continuous random variable? The equations are sort of transparent. For example, the expectation is then, remember we had the sum, now it's the integral over x, p of x. The variance is the integral over the difference between x and the expectation of x times p of x, and similar the covariance definition. So the first and good news is don't worry too much. It's it doesn't change much, at least on the level we are discussing it. If you're deeply into the mathematical theory, you might see a lot of differences. Yeah, I'm also covering maybe the most important distribution, so the one which is defined, or density, normal. So density specifies that it's a continuous variable distribution. It's a more general term. So we write it like this. So p of x, so this is now a continuous random variable. And we write it in this, so normal or Gaussian, so this normal symbol of x conditioned on or given the mean value of this distribution. So now we are talking about everything is one-dimensional, no? So there's one parameter here. And we have this sigma xx, which in this case it's one-dimensional, is simply the variance of x. So this is the expectation of x, and this is the variance of x. And it's written by this formula, 1 over square root 2 pi, so this is just a number variance, times the exponential function, times minus 1/2, then x minus the mean transposed. So in this case it's just one number, so we don't have to take the transposed. Again, this is just one number because it's just the variance, so 1 over the variance times x minus mu. So these are the same quantities here. If we are talking about vectors, then this would be the transposed. But now everything is one-dimensional, so this matrix is just this one number, and the transposed we don't need. And of course, you can write the same thing also for another random variable y, only that we have subscript y now. And now, of course, we are also interested in the joint distribution. And first, we are considering that the two random variables are independent. And then we can define z as a quantity with two components, x and y. And the mean is simply the mean of the individual distributions. And the covariance, which is now really a matrix, has these variances on the diagonal and then 0 on the off-diagonal. And we write now P of z equals, again, normal distribution evaluated at z with mean mu, which is now a vector, and covariance matrix sigma, which is now a real matrix, but this one. Then this factor in front becomes 1 over 2 pi to the power of m divided by 2. So in this case we have m equals 2, so this would be just 2 pi. And then square root of this matrix here. And this sign means the determinant of the matrix, so in this case the product of these diagonal ones. So we don't have to deal too much with determinants and so on, just you just have to understand that this is the determinant, which in the simple case is the product of the diagonals. And now we have the exponent, and so now we have 1 minus 1/2 z minus the mu value, and here now we need the transpose because it's now a vector. Same vector here is on the right side, and in the middle we have the inverse of this covariance matrix, which is again diagonal. In this case would have 1 over the variances in the diagonal. So m is a dimensionality, here it's 2. This sign means the determinant, and in this case it's just the product of the diagonals. So this is how a Gaussian distribution looks in one dimension. So we have this mean value or the expectation here, and then we have this typical Gauss curve behavior here, and this arrow here indicates the standard deviation, so the square root of the variance, which has this sort of geometric interpretation. It sort of tells you how wide this Gaussian is. Or in 2 dimensions, now x and y, we have again a mu vector this time, and this is sort of the area of, or the region of the same amplitude of the Gaussian. And if you want to plot it, this is how a 2-dimensional Gaussian would look like. And I'm sure you have seen these things before. Right? Now, if the two random variables are dependent, of course, then the covariance matrix is a full one. We have the variances on the diagonal, and these two values are the same. So sigma xy is the same as sigma yx. And we use essentially the same formula. P of z is the normal distribution centered or evaluated at z, centered at mu with covariance sigma. So everything else stays the same. Only that we have this off-diagonal term, which is the covariance. The determinant is the diagonal minus the product of the off-diagonal. And this can also be generalized to more than 2 dimensions. So you should get used a little bit to this formula. But you don't have to remember how to calculate the determinant, for example. So this shows the joint distribution and the marginals. The blue and the red one. That's another nice Gaussian distribution. And this is the last slide. So this equation sometimes comes in handy. No? So we know what the joint distribution is, this one. What is the conditional distribution? And so it turns out, and I don't derive it here, that the conditional distribution x given y is a normal distribution again, evaluated at x. And the expression for the mean now is a little bit more complicated. It's the mean of x plus the covariance xy times the inverse of the covariance yy. So this is these are the diagonal term. This is the diagonal term. This is an off-diagonal term times y minus the mean of y. So this is the mean term, and then we have the variance term, because this is one-dimensional. So it's the variance of x minus the variant of xy, so the covariance, times the inverse of the variance of y times the covariance again. So this is one of these formulas you don't have to remember, but you know where to look it up when you need it. No? And of course, the other way around, it's symmetrical. You can use the equivalent formula here.